Okay, so today I'd like to define and explain some things about continuous mappings from one topological space onto another. So let me give a definition. It's a good place to start. So for topological spaces, x tau and y tau 1, a mapping f, which maps from the set x to the set y, is said to be a continuous mapping when we have that for every open set in y tau 1, for every open set in the space we're mapping to, we have the pre-image of that's f to the minus 1 of u, is an open set in our initial space x tau. Okay, so remember, this is the sort of topologist's definition of a continuous mapping. We're going to see later that this does indeed correspond to what people think of as a continuous mapping from real numbers to real numbers. So that's a much more restricted case, which is just a special case of this. So this is very important, and let's just have a look at a diagram to explain what's going on here. So this represents the space X, and let's draw the space Y here a bit differently. So here's Y, and this is our mapping F, which sends us from X to Y. Now, our requirement for continuity is that if we take any open set at all in the space Y, so I'll use a dotted loop to indicate an open set, and then we look at the pre-image of that open set, by which I mean the set of all points in X which get mapped to points in that open set U. And so let's call that open set f to the minus 1 of u. Well, that better be an open set in X. That's our required condition in order for f to be a continuous mapping. Okay, so there you have it. That's our definition. Okay then, so those of you who have done real analysis will have seen a very different looking definition of continuity, and I don't really want to talk about it, but I think I should just mention it. So block your ears up, everyone who's not familiar with real analysis. But in real analysis, the definition of continuity is like this: a mapping from the real line to the real line is said to be continuous when we have that for every point on the reals and for every epsilon greater than naught, there exists a delta greater than naught, such that when the distance between x and a on the real line, this is the absolute value, by the way, absolute value sign. So when this is less than delta, that always implies that the distance between the images f of x and f of a is always going to be less than epsilon. So basically what it means is that if you give me a value of delta and a point on the line, I can give you a value, if you give me a value of epsilon and a point A on the line, I can give you a value of delta such that every single point that's within delta of your point A has an image which is within epsilon of the image of the point A under this mapping F. That's the real analysis sort of definition of continuity. Now, I just gave a different definition of continuity, which is valid for all topological spaces. And this is actually just a special case of the other. So if you take the definition I just gave, so I'm just going to erase this now just to emphasize that I don't really want to focus on it. So I'll call this the real analysis definition of continuity. So just before this I gave a better definition of continuity, which was valid for any mapping from a topological space x tau to a topological space y tau 1. And if you remember, the important thing is that for every open set in tau 1, we want that the pre-image of that open set is an open set of the original space. Okay, so this is the definition of continuity that we're going to work with. But it turns out that when this is equal to the real line with the Euclidean topology, and this is equal to the real line with the Euclidean topology, then this definition here of continuity is equivalent to the real analysis definition of continuity, as it should be. Okay, so this thing here is a true generalization of the idea of continuity from real analysis. Alright then, so let's look at some examples of continuous functions. So I know I've said it about 3 times, but I'll say it just once more. We are sticking with the idea of continuity from topological spaces. Okay, so now let's consider the real line with the Euclidean topology. And one result that we have is that a mapping F from the real line to the real line, again with Euclidean topology, the mapping which is defined such that for all x belonging to the real line, we just have that f of x equals x. Okay, so it's a really boring mapping. We have that this is continuous. So basically this is just the identity function. So how do we prove that this is continuous? Well, it's a very, very easy proof. Basically, the proof is just that for every open set, so for every open subset of the real line, we have that the pre-image of that open subset, so f minus 1 of u, is just equal to u itself, because this is the identity mapping, so nothing changes. And this, of course, is also going to be open. So the pre-image of open sets are open sets, therefore this mapping is continuous. Okay then. Let's look at a slightly more challenging example, but not much more challenging. So a similar kind of thing, we're talking about mappings from the real line to the real line, but now we're going to look at the mapping which is defined such that for every real, we have that f of x is equal to some constant real number. So maybe this mapping sends every real number to 2 or something like that, whatever value c takes. So we want to show that this is continuous. Perhaps you'd like to pause the video now and see if you can prove this. Okay, so the proof, or a proof, is that what we're going to have is that for every open subset of the reals, we're going to have that the preimage of this open subset is going to be of this form, okay? It's going to be equal to the set of all reals if C is a member of that open set U, and it's going to be equal to the empty set otherwise. Okay, so what this is basically saying is that, well, the reasoning behind this is that if our set contains C, then since every single point was mapped to C, the preimage of that set is going to be every single point on a real line. And if our chosen set U does not contain C, then no points were mapped into it, so the preimage is empty. And so it's fairly obvious now that both of these are both open in the Euclidean topology. So since the preimages are open, this is a continuous mapping. Okay, now let's look at a slightly more interesting example of another mapping from reals to reals. So here we're going to see that our kind of definition of continuity is, I think it's nicer really than the real analysis style one. It's actually easier to work with even when we're talking about reals. So let's consider a function which is not continuous now. We're going to consider this function here, f of x, and it's going to be equal to x if x is less than or equal to 1, and it's going to be equal to x plus 1 otherwise. So this is just another function f which maps excuse me, that's what I wanted to do. Okay, so it's another mapping f which maps reals to reals. Okay, so let's draw the plot of this function. Okay, so this is x and this is f of x. Now here is 1 and here is 1, so, and here is 2. So here's how our function goes. It's just the line f of x equals x up until it gets up to this value of 1, and when x is 1 it jumps up to 2 right here, and it carries on like this. So it's obviously not a continuous function, it has this jump on it. How do we prove it? Well, let's consider this open interval here between 0 and 1.5. Okay, so what is this? Well, this is just the open interval for all the numbers which are greater than 0 and less than 3/2. Okay, and what we're going to do now, we're going to think about the preimage of that. So that's an open interval. That's obviously an open set in Euclidean topology. But what about the pre-image? Well, a little bit of thought should convince you that the pre-image of this is actually the set of all reals which are greater than 0 and less than or equal to 1. Okay? Because this mapping here, it sends every single point, the set of points which are such that if we trace them up to the function like this and then send them across, they end up landing in this vertical interval between 0 and 1.5. The set of all those points on this diagram are here. They go all the way up to 1 inclusive, because 1 gets mapped to 1, which is inside here. So indeed this is the pre-image of the open interval between 0 and 1.5, and this here is not open, and so we've found an example of an open set that's pre-image is not open, and so that implies that f is not continuous. Okay, so that's good. This is an easy to work with notion which agrees with our common sense understanding of what continuity means. Let F be a mapping from a topological space x tau to another topological space y tau 1. So now we have that F is continuous and that's going to hold if and only if we have that for every point of our original space X and every open set of our image space Y, which has an image of the chosen point X inside it, we have that there exists a open set V within our original topology, topological space associated with X, which is such that our point X belongs to that open set, and also the image of that open set V is actually contained within U. So this is actually analogous to the real analysis definition of continuity, except that it holds for more general topological spaces. Okay, so here's another proposition which we've already seen quite a lot of before. And so here's how it goes. Suppose that we have 3 topological spaces. Firstly, let's say we've got a topological space x tau, and then we have a continuous mapping f from that topological space to another topological space, which is called y tau 1. And let's suppose that we've got another continuous mapping G to that doesn't look much like a G. Let's do another. Okay, to another topological space z tau 2. Okay, so these things here, these are continuous mappings, and these 3 things here are topological spaces. And now our claim is that the composition which is written hang on a second. Okay, so the composition G composed of F, that means the mapping you get from first applying F and then applying G is a continuous mapping from the topological space X tau to the topological space Z tau 2. And actually, we've already proved this. So remember when we were talking about homeomorphisms in the last lecture, and you've probably noticed by now that a homeomorphism is precisely the same thing as a one-to-one onto mapping, which is continuous and which has a continuous inverse. And so when we were proving that homeomorphisms have this transitivity feature, which basically means that if space A is homeomorphic to space B and B is homeomorphic to space C, then A is homeomorphic to space C. When we proved that, we actually established this fact when we were showing about condition 3 of the homeomorphism thing holds. But anyway, let's just prove it again, just to recall. So it's a very simple proof. Basically, let's just suppose that we've got an open set U which belongs to tau 2. So this is an open set of this space. Now, since G here is a continuous mapping, that means from a definition of a continuous mapping that the pre-image of U is going to be an open set in a topology tau 1. And now, since F is a continuous mapping, we're going to have that the pre-image under F of this is going to be an open set in the original space tau. And now the important thing to notice is that this is actually equal to the inverse of the composition, G composition F of U. Okay, why is that? Well, basically, I think I already said this last time. Think of F. That's the first thing you do when you apply this composition. So think of that as something like putting your socks on, and think of G like putting your shoes on. So the opposite of that is first taking your shoes off, as in applying G inverse, and then taking your socks off, which is applying F inverse. So when you inverse a composition, you do the operations in reverse, but you do the inverse of the operations in reverse order. Yes, so that completes our proof. We've just shown that the pre-image of an open set under our composite map is an open set. Okay, so let's go for another proposition then. Okay, so here's our proposition. And what it says is that a mapping F from a topological space X tau to a topological space Y tau 1 is going to be continuous if and only if we have that the inverse of hang on, that's not the right way to say it. If and only if we have that for each closed set of the topological space y tau 1, we have that the pre-image of that closed set is closed in the original space x tau. Okay, so basically it's just like we're saying, it's just like the way we define continuity with respect to open sets, except replacing the word open with the word closed. So what's the proof to this result? Right, the key to understanding it, so let's start writing the proof. The key to understanding it is to know that the well, how can I write it? F to the minus 1 of, say, okay, so let's say that R is some subset of Y, okay? So the point is now that F to the minus 1 of Y minus R, in other words, the pre-image of the complement of R, is equal to the complement of the pre-image of R. So it's equal to X, take away F to the minus 1 of R. Okay? And that holds for any subset of Y. So what is this statement saying here? What it's saying is this. We've got this mapping from the space capital X to capital Y. And if we take any subset R of capital Y, and then we look at the pre-image of the complement of R, that's this here, okay? So what does this say? Well, what it says is this is the set of all points in X which get mapped to things outside of R. And of course that's going to be equal to this, which is just equal to the set of all points in X which don't get mapped to things inside R. So we're always going to have that this expression holds. Now we can use this to our advantage in proving this proposition. So I'll rub out the actual proposition to make some space. Right then. Now we can do some writing. So let's start by proving this thing going forwards. So we'll start by proving the condition going this way. So suppose S is closed. Now we're going to let R denote the complement of S, and that's going to be open. Well, we can just write it like this. It's going to be a member of the topology. No, in fact, let's just not write it like that because I've got a problem with the screen up there. So R is going to be open in our image topological space y tau 1. And now that implies that f to the minus 1 of R is going to be open in our original topology, tau. So our original topological space X tau. And now what we're going to have then is that the pre-image of this closed set, which was S, well, that's going to be equal to the pre-image of the complement of Y with R, and that's going to be equal to, because that's another way of writing S, is Y is the complement of R. So basically what we're saying is that if this is Y, this space is Y, if this space here is Y, then Y has two parts. It's partitioned into two parts, R and S. Okay, so the complement of R is S and the complement of S is R. So the pre-image of Y minus R, by this red writing down here, that's going to be equal to X take away the pre-image of R. Now we know that this is open. We just argued that. So we must have that this whole thing here, as the complement of an open set, has got to be closed. So we've just shown now that the pre-image of our closed set is closed. So we've proved that the argument holds that way. Okay, so we've just shown that if our mapping F is continuous, then the pre-images of closed sets are closed. So it remains to show that if our mapping is not continuous, then the pre-images of closed sets are not always closed. That will complete our if and only if statement. So to finish the proof and prove it this way, essentially, we're going to suppose that F, which is mapping X tau to Y tau 1, is not continuous. Now what that means then, it means that there must exist an open set in tau 1 which is such that the pre-image of this open set is not open in tau. Now what we're going to do is we're going to consider the complement of this pre-image. So we'll define S to be equal to the complement of it, Y take away R. Now what we're going to have is that the pre-image of, okay, so note that this is going to be a closed set. It must be closed in tau 1 because it's the complement of something which is open in tau 1. Now well, we're going to consider the pre-image of S now. So let's write that out totally. It's going to be the pre-image of Y minus R. and by the red writing, it's going to be equal to x, take away the preimage of R. Well, we've just showed that this is not open in the original topology, so that implies then that this whole thing is not closed. Oops, not in tau 1, just in tau, excuse me. In tau, not closed in tau, okay? So what we've essentially shown now, in a nutshell, is that if f is not continuous, then there exists a closed S in y tau 1 such that the preimage of S is not closed in our original topological space x tau. And that completes our proof. We've shown that if a statement holds, if f is continuous, then our statement holds. If f is not continuous, our statement doesn't hold. Okay then, so when we have a mapping f, which is from a set x to a set y, and when we have that a is a subset of x, then when we say the restriction of f to a, what we mean is the mapping, we call it, say, G. Let's call it G. And it's a mapping from A to Y. And it's such that for every member of A, we have that G of X is just equal to F of X. So it's basically the mapping which is defined just the same way as F is. It's just that it's only defined on the elements of the subset A. Okay then, so let F, it's a mapping from X to Y, so it's a continuous map from the topological space X tau to the topological space Y tau 1, as usual. Okay, and we're going to let A be a subset of X. And now we're also going to let tau 2 be the subspace topology. Defined on A. Okay, so remember this, it's from quite a few lectures ago. So essentially what we've got here now is that we've got that A tau 2 is a new topological space, and the open sets of A tau 2 are equal to the open sets of X tau, except that those open sets are intersected with this subset A. What we now have is that if we let G be, well, G is going to be a mapping from our subspace A tau 2 to the topological space Y tau 1. And we get G, it's just basically the restriction of our mapping F to the subset A in the sense that I've just described. And now our result finally is that G is continuous. So I think a diagram is in order here. So here is our original topological space x tau, and here is our space y tau 1. Now suppose we've got some subset of x which is called A, and so we give that the subspace topology, and we're also supposing that we've got a continuous mapping F which is from x tau to y tau 1. Okay, so what our result says now, it says that if we now consider the mapping, which is just the restriction of F on this subset A of X, so we'll call that mapping G, then G is actually going to be a continuous mapping from the subspace A tau 2 to the image space Y tau 1. That's what our result says. Okay, so now I want to start working towards something called the Intermediate Value Theorem. So we're going to change track a little bit and talk about things like continuity and fixed points and how those interplay with continuous mappings. Okay, so we're going to change gear a little bit now and work towards something called the Intermediate Value Theorem. So this is interesting stuff. We're going to have a look at how continuous mappings interplay with connected topological spaces, and then we're going to move towards establishing some fixed point theorems. So this is actually something I really enjoy because we're getting close to proving something called Brouwer's Fixed Point Theorem, which is a really nice result in topology. Well, I'll talk more about that later. So for now, let's just establish this important proposition. I'll call it proposition star because we're going to refer back to it later. So what it says is that we're going to let F be a continuous mapping from the topological space x tau onto, here it's an important word, onto the topological space y tau 1. What do I mean by onto? I mean basically that, I know I've written it like this, but essentially F is mapping from the set X to the set Y, and it has the property that every element in Y has at least one element in X which is mapped to it. So like the whole of Y gets covered as the image of the set X. Okay, so it's an onto mapping onto this topological space which is connected. Now we have the important result that if x tau is connected, then y tau 1 is connected. Okay, so let's do a proof. So I'll go for a proof by contradiction. We'll suppose all our statements are so, except that y tau 1, let's suppose it's not connected. Well, according to our definition of connectivity, What that means then there's going to exist a clopen set, a clopen set U belonging to the topology tau 1. So this set U is subset of Y, which is open and closed, and it's going to be such that it's not equal to the empty set, and it's not equal to the whole space. Something in between. Okay then, so let's find our contradiction. Whoops. Now, since our mapping is going to be continuous, we're going to have that the pre-image of U is going to be open in our initial topology, not tau 1, just tau, okay? In fact, it's going to be clopen within our original topological space, x tau, because the same argument holds for its complements. Now, also, the pre-image of this set U can't be empty. Why not? Well, because F is an onto mapping, and U was a non-empty set. So U is a non-empty set of Y, so it has some points, and those points have to have had some points that got mapped to them. So the pre-image can't be empty. Also, the important point is that we also have that the pre-image of U can't be equal to the entire space. Can't be equal to the entire space X. Why is that? Well, because since F is an onto mapping, we know that the image of X is equal to Y, and we know that U is not equal to Y. So U cannot be the image of X. So the pre-image of U cannot equal X. And so now we've just showed that the pre-image of U is a clopen subset of x tau, which is not equal to the empty set and not equal to a whole space. So we've just shown then that the space x tau is not connected. And that finishes our proof, because we've just contradicted this assumption. So we've basically shown that if we suppose y tau 1 is not connected, then we get a contradiction. So this cannot in fact be true, and so that means our result must hold. Okay, so what we're going to do now is introduce weaker concepts than continuity. So we call it path connectedness, and it's weaker than continuity, and it's easier to use. So the definition then, we'll say that a topological space x tau is path connected when for every pair of distinct points in the space there exists a continuous mapping F, which is from the unit interval to the topological space which has the property that it sends 0 to A and it sends 1 to B. And so we call F a path joining A and B, or joining A to B, if you like. So this is a really nice idea. We've got some space here, some topological space x tau, and here's our point A, let's say, and here's our point B. So we can really think of this as a sort of path, and for example, if we pick the point 0.75, then we can associate that with, that's going to be where the point 3/4 gets mapped to by f. So it's going to be a point somewhere along this path. And then the point 0.576 is going to be further along this path. So we can sort of think of the value of f of x, it's not really right, but we can think of it as a point which is sort of a fraction x along this path from A to B. So anyway, enough about intuitive definitions. What about the properties of this thing? Well, the important idea is that every path connected space is connected. Okay? So if we can connect every pair of points by one of these paths, then the actual space has to be connected. So let's establish this. So let x tau be a path connected space. And we'll go for another proof by contradiction. So we're going to suppose that x tau is not actually connected. So what that means then is there exists a clopen non-empty, non-full space set U. Okay then. Now we're going to find our contradiction. So we're going to choose A belonging to U, and we're going to choose B outside of U. Now, since our space is path connected, we've got to have one of these paths from A to B. In other words, there must exist a mapping F from the closed unit interval onto our space, to our space, which is going to be such that it sends 0 to A and it sends 1 to B. Now the trouble is though, let's consider the preimage of this clopen set U. Well, that's going to be a clopin set of the closed unit interval. And in fact, it's going to be such that it's not equal to the whole unit interval, and it's not empty. And so we have that the closed unit interval is not connected, and that's wrong. So that's a contradiction, and that finishes the result. Because since we've just shown that this statement here, we're supposed to be assuming that X tau is not connected. Hopefully I said that. I wrote it wrong there. But anyway, when we assume that X tau is not connected and we fulfill the argument like this, we get a contradiction. So this must in fact be wrong. It is wrong to say that X tau is not connected. So it must actually be connected. And that finishes our proof. Okay then, so just before we can get to our intermediate value theorem, we've got to go for another definition. So this is a formal definition of an interval of the real line. So suppose we've got a subset of the real line. Now we call it an interval when we have the special property that for every x, y, and z in the line, in the set, in the line, excuse me, let me start again, okay? So for every x and z belonging to S, and for every y belonging to the reals, which is such that x is less than y, which is less than z, we have that y belongs to S. So essentially we have the property that if a point is between 2 points in an interval, then it must also be a member of an interval. That's our defining characteristic of an interval. And our proposition, which is going to be useful for us today, is simply that a subspace of the reals is going to be connected if and only if it's an interval. So let's call this proposition I, because we're going to use it today. So we give it a name. So a subset of the reals is connected if and only if it's an interval. What's the proof? Well, it's easy to prove that all intervals are connected. I'll leave that as an exercise for you. You can use some of the techniques we've been talking about when we first defined connectivity. Now, proving the converse is a little bit more challenging. So we're going to go for a proof by contradiction. So we're going to suppose that S is connected. And now we're going to prove that it has to be an interval. So we'll assume the opposite. We're going to suppose that it's not an interval. So we're going to suppose that we've got a couple of points x and z belonging to the set, and another point y, which is a real number. And we're going to suppose that y is between x and z, but y is actually not a member of S. Okay, so this writing in red is essentially just saying assume that S is not an interval. Okay, so now what happens? Then what we get is that if we look at the open interval, well, the open set from minus infinity to y, let's take the intersection of that with S. Well, that's going to be equal to the set from minus infinity to y with a closed set intersection S. So that's inclusive on y. That's because y is not actually a member of S. Let me just write this a bit more clearly. So these two things are going to be equal because y is not in S. And this set is going to be clopen. It's open because it's the intersection of, because it's the intersection of this set here. It involves this set here, which is open, and it's closed because it involves this set here, which is closed. So now what we want to do we want to show that S is not connected. So this set here is clopen in S. And now we just want to show that this clopen set is proper and non-empty. So it's going to contain the point X. That's going to be contained within this set. Let's give the set a name. Let's call it A. So this implies that A is not empty. And also Z is a point of S which does not belong to A. So that implies that A does not equal to S. So this set A here is clopen in S, but it's not equal to the whole of S, and it's not empty. So so S is not connected. So there we go. Our initial statement here, which was supposed to be suppose S is connected, we've just contradicted it. So again, we've just shown that this writing in red leads to a contradiction, which finishes our proof. So now we get to our big theorem, the Weirstrass Intermediate Value Theorem. So it's a famous result. And what it says is that if we have a continuous mapping from a closed interval to the set of reals, which is continuous, then what we have is that for every real p, which is between f of a and f of b, then there's going to exist a point c, which is in this closed interval from a to b, which is going to actually get mapped to this point c. Sorry, to this point p. So it's a really cute result. Basically, it says that if we look at the images of the endpoints of our closed interval, and then we pick any point which is between those two images, then we can find a point in our closed interval that gets sent to that point between them. In other words, we can find something that gets mapped to an intermediate value. So we've already pretty much laid down the groundwork for the proof of this. So the proof, well, since we've got the, well, we must have that our closed interval is connected. Every closed interval is connected. And so proposition star says that f is connected, that f of the closed interval is going to be connected, and proposition I implies that the image of this closed interval is going to be an interval, and so now maybe I'll start writing up at the top again. I don't want to run out of space. Change color as well. Now obviously f of a and f of b are going to belong to the image of this closed interval a to b, and so what we have then is that if p is going to be between f of a and f of b, then p has got to be a member of this, of the image of this closed interval. That holds by the connectivity. And so basically what that means is that P is going to be equal to f of C for some C in the closed interval from A to B. That's pretty much exactly what this says. So there we have it. This is our intermediate value theorem proved. So there are some important corollaries to this intermediate value theorem. So one pretty straightforward implication is that if we've got a mapping F, again from a closed interval to the reals, and it's continuous, and if it's such that it maps A to a positive number and it maps B to a negative number, then of course there's going to have to exist a point somewhere in the closed interval which is such that that point is mapped to 0. I mean, this really seems kind of obvious, but it's very nice to have a completely rigorous proof of this when you consider about kind of the topological subtleties of the real line. And now another really kind of powerful implication of this is the next corollary, which is really a fixed point theorem for one-dimensional space. So here goes. And this is really a fixed point theorem, okay? So once again, well, we're going to let F be a continuous mapping. Whoops. So it's a mapping from the unit interval to the unit interval. And our claim then is that there's going to exist a point in the closed interval, the closed unit interval, which actually gets mapped to itself. Okay then, so what's the proof to this interesting result? So just to sketch this diagrammatically, what it basically says is that let's here is Z and here is f of Z, okay? And so this is the function this is a function with vertical height equal to the horizontal length. So this is basically the function Z. And say this is 0 and this is 1. What our result says is that if we look at any mapping at all, like this, it has to cross this dotted line at some point. Okay, so what's the proof? Well, if our mapping sends 0 to 0, or if it sends 1 to 1, then obviously our results going to be true in that case. So we can just suppose then, since we want to consider the other cases, we can suppose that f of 0 is positive, and also that f of 1 is going to be less than 1. That's completely reasonable. So I'll just start again from the top to finish the rest of the proof. So we're going to define another mapping now. So we're going to let G be a mapping from the unit interval to the reals, which is going to be such that G of x is just equal to x take away f of x. So what we're essentially trying to show is that this mapping has a 0. Now, since f is continuous, G is going to be continuous, and also G of 0, what's that going to be equal to? Well, that's going to be equal to minus f of 0, which, as we've just argued, is going to be, well, in the case we're going to consider, it's going to be a negative number. And G of 1, I think you can probably see where this is going. This is going to be equal to 1 take away f of 1. This is a nice proof. And since we've already said that f of 1 has got to be less than 1, 1 minus f of 1 has got to be positive. And so now, now the last corollary is going to imply that there's going to exist some z in the unit interval, which is going to be such that z gets mapped to 0. And that implies that f of z equals z. And that's the end of our proof. So we've proved that every mapping from the unit interval to itself has a fixed point. So this is the one-dimensional version of Brouwer's Fixed Point Theorem. So Brouwer's Fixed Point Theorem, it actually goes further than this, but one thing it implies is that the same is generally true if we have a mapping from the unit n-dimensional cube to itself, a continuous mapping, that it must have at least one fixed point. But I'm not going to prove that here. So actually, if you want to find a proof of it, there's quite a nice proof in the book Introduction to Set Theory and Topology by Kuratowski.